Trigonometric identities. The goal, make sure you guys get it down, is that you'll be able to use identities to solve problems. Now, last week we just kind of dealt with your basic type of equations that deal with trig functions. Okay, accept those as a blessing. They give you those easy ones. Okay, because they could give you some more challenging ones, like the ones that we'll deal with today that do involve identities to be able to solve solve equations. Okay, so that's what we're talking about today, the different types of identities. We've already actually talked about one identity already, the Pythagorean identity. It was within the trigonometry notes. Does anybody remember the Pythagorean identity? It's back in your trig notes.
Sine squared.
Say it again.
Sine squared plus cosine squared plus tangent squared.
I'm missing the end part.
Equals tangent squared.
Equals tangent squared? No, not tangent.
It's
Equals theta.
Not theta.
What?
It's 1. We talked about this back when we first did, I believe it was part of your printed notes during that unit. This is your Pythagorean identity. When you have an angle that's in standard position, we know that cosine is x, sine is y. And so basically it's old school Pythagorean theorem, just dealing with an angle that's within your unit circle. So that's the Pythagorean identity. This is like one of the main ones that you definitely want to make sure that you know, because more than likely this is probably used the most out of all of your identities. Okay, so please make sure you get that one down. All right. Do realize that it could also, be cosine squared x plus sine squared x equals 1. Do realize that cosine and sine can switch places. Also realize that this can be manipulated. Okay, you could have that, cosine squared x is equal to 1 minus sine squared x. Okay, do realize that this is also the Pythagorean identity, just rewritten, solved for one of your particular trig functions. Sine squared x equals what? 1 minus cosine squared x, okay? So you could take that one Pythagorean identity and derive 2 others, okay? So don't think that that is the set one. Do realize that you can also have, cosine squared x and sine squared x, okay? Some other identities that are your double angle identities, all right? These are when you have a 2 attached to your variable. Okay, so instead of just being cosine x or cosine theta, it's cosine 2 theta, not squared. It's a big difference. Okay, there are 3 different types of identities for cosine. You'll know you're not going to use all 3 at the same time. You're basically going to pick which one of the 3 best fits your problem. Okay, and you can basically substitute any one of the 3 in for cosine 2 theta. It really just depends on what problem you're dealing with. And you'll see in a second, why one is probably better than the other. And then you have sine 2 theta, or sine 2x, or sine 2 alpha. It's 2 times sine theta cosine theta. And these identities, again, are used to help you solve equations, okay? These are used to solve equations. They can make the problem a little bit more simpler. It allows you to basically substitute in any one of these for cosine 2 theta or sine 2 theta, so that way maybe you can use the quadratic formula or, actually, be able to solve the problem, because it depends on the situation that you're in. So you can use that to your disposal. So we're going to look at an example. Everyone done write it down? Okay, I'm trying to fill it here. We have given that sine x equals 3 over... Given that sine x equals 3 over 4, and x is in between 0 degrees and 90 degrees, we are going to find the exact values of those 4 So, in this particular case, we're given two important pieces of information that sine x is 3/4 and that x is in between 0 and 90 degrees. Now, they give you that little bit of information there because it's basically telling you that if you were to have an angle where sine was 3/4, that angle is located in that first quadrant there, okay? So if you wanted to, you can kind of do a quick sketch of an angle, okay? And this does make a right triangle with your x-axis. And we know sine to be what over what? Old school, trig, thank you, opposite over hypotenuse. So if this is 3, then we know that this is 4. And if we're looking for the cosine of x, we could do Pythagorean theorem to find that missing side, okay? You guys do Pythagorean theorem real fast to find out that missing side. And these are exact values here, so no calculator or anything. So find that other side. So use the Pythagorean theorem. What did you guys get for that side? Yes? Square root of 7. So then you can use what you know about cosine being what over what? Adjacent over hypotenuse to find out that cosine of x equals square root of 7 over 4. Okay? That's one way. That's using trig here. Okay? You can also use your identities to figure this out as well. Okay? Now, cosine x. At the identities that we've already seen today. Okay? At all the identities that we've seen today. Your Pythagorean identity would be the most helpful to figure this one out. Because if you think about it, the other two identities that we talked about, the double angle, has a cosine 2x or cosine 2 theta and the sine 2 theta. That really is not going to help us out here considering the only piece of information we know is sine x. That's all we have. Okay? So this would be the only identity that we could use to help us figure out the cosine. Okay? I'm showing you guys another way you could do this. Alright? Since you know that sine x is 3/4, you can actually plug that in for sine x and square it. And basically, it's just an equation that you solve for. What's 3/4 squared? 9/16. You would subtract what? 9/16. So I'm trying to basically solve for cosine x, so I need to get it by itself. What would that be? What's 1 minus 9/16? 7/16. And then to get rid of the square, you would take the square root. So you have the square root of 7 over square root of 16, which is 4. The only thing you have to remember is that when you take the square root, it is plus or minus. But because we're in the first quadrant, we only want the positive. So either way, you can find square root of 7 over 4. Now do realize that sometimes defaulting back to the Pythagorean theorem might not always work. So you would have to use that identity. That's why I showed you both. Okay? Now B says cosine 2x. We're finding cosine 2x. Well, look at your formulas, right? For cosine 2x, there's 3 different ones, right? Which one do you want to use? The first one. Why the first one instead of the other two?
The other two have cosine still.
But then we find cosine?
Yeah, but the first one is just easier because you don't have to
plug
square
everything
root,
in.
you just plug it in.
We just plug it in. Okay. Now mind you, we already found cosine, so cosine's done. Like we found that we can use that. Okay. So realize you can use any one of these 3 because your first thing you had to do was find cosine, right? So now we can honestly use any 3. All right. Now I'm glad you guys did say the first one. You guys said because it's easier. Well, technically you already did the work to find cosine, so honestly any one of them would be easy. But at least this way, by using the first one, if you did find the wrong cosine, you at least have a chance of getting this one right. So you understand that? Because we were already given sine. So, using that formula of 1 minus 2 sine squared theta, or sine squared x, we'll just plug in 1 minus 2 sine x is 3/4, so we plug that in, and we square it. Order of operations says we do what first? The square, so this becomes 1 minus 2 times. When we multiply by 2, that becomes 1 minus. And then when we do 1 minus that, it becomes
-2 or 16 or
or you said -1/8. Questions? Mm-hmm. Did you find the exact value of cosine 2x? So any one of the formulas, you plug in the value of either sine or cosine, depending on which one you use, and the simplify. And that is the exact value. Questions so far? Formula, plug in. Sine 2x. That formula is what? So 2 sine theta cosine theta, or in this case we'll use x, since that's our variable. We already know what sine is, so we're going to plug that in. And we found what cosine is. Now, on problems like this, you definitely want to make sure that you found the right cosine, okay? So we double check. We did 2 different ways, got the same answer, so we're pretty good. And we'll plug in square root of 7 over 4. And then we just multiply. When you multiply all those together, what do you get? When you multiply all these together, what do you get?
6 squared root 7 over 3 squared 7.
6 squared root of 7 over, careful,
Oh.
16. This reduces, doesn't it?
3 squared root 7 over 8. If you reduce that to multiplication.
Because it's the exact value, so we wouldn't go through any decimals or anything like that. We could simplify the square root of 7, we would, but we can't. Lastly, tangents to x.
Would we be able to do the double angle identity of sine over where the cosine is?
Mm-hmm.
So it'd be like sine 2x over cosine 2x.
Exactly. Your quotient identity. The tangent is sine over cosine. You can use here. So tangent 2x is the same thing as saying sine 2x over cosine of 2x. And we just found both of those, didn't we? Okay? So we're going to plug those in. So sine of 2x was 3 root 7 over 8. And cosine of 2x was a -1/8. We have a fraction within a fraction, so we multiply by the reciprocal. What's the reciprocal of -1/8? And then we'll multiply. But what do you notice? The 8s and the 8s will do what?
Cancel. So it's just 3 root 7.
Careful.
-3 root 7. I wrote that down.
Okay? So, because I was running out of space, I just went ahead and multiplied by the reciprocal opposite side of the numerator. Okay? So there's no more denominator. And that's how we got -3 root 7. Questions? Okay? We're going to do another one. This is given that cosine of theta equals 4/5 and theta is in between 3 pi over 2 and 2 pi, find the exact values of sine theta and cosine 2 theta. Okay, shorter one this time. Let's use our Pythagorean identity to figure out sine though. What's our Pythagorean identity? These for the notes. Okay. This is the, manipulated Pythagorean identity. Okay. We know cosine is, so we're going to plug in 4/5 and we're going to square it. So then that becomes 1 minus 16 over 25. What is 1 minus 16 over 25? 9 over 25. And how do I get just sine theta by itself? And remember, whenever you take the square root in an equation, and you always get plus or minus, in this case it's going to be 3/5. But which one is it?
It's the negative one,
And why?
because we're in the fourth quarter.
Because we're in the fourth quadrant, okay? And because we're in the fourth quadrant, sine, which is the y values, is negative. Okay?
All the problems like these would be in the non-calculated portion.
They could also have some of these in the calculator portion, but if they want you to find the exact values, for sure, they will be in the non-calculator. Let's do cosine 2 theta. Which identity do you want to use? The first one? When you count the wrong sign though.
You should do the second one.
Follow through point, follow through.
You should do the second one, which is 1 sine squared theta
Plus 1?
minus 1.
Because heaven forbid, and sometimes they don't reward follow through. Sometimes they don't. They're more likely to do that in the other class.
That's why you must face in your answer that you got it right.
Alright. So we already know cosine is 4 over 5, so we plug that in, square it, and we'll subtract 1. What do you first? Square. So what is 4/5 squared? What is that? 7 over 25? Careful. Oh, sorry, no.
That's what I got.
Alright, this one's on you. Find those 4. You do about 6 minutes. Alright, so it says tangent equals 3 over 4, and theta is in between 0 and pi. We had to find each value. So first off, how'd you guys start?
First
Triangle. What quadrant?
First one.
First, and it could only be the first because of what reason? It's positive and positive, and even if it was a negative and negative, which still makes a positive tangent, it still wouldn't be in the second quadrant, it would be in the first. So tangent is 3 over 4. So then that means that hypotenuse in that right triangle is what?
5.
5. So that means that sine theta is,
3
and cosine theta is
4.
simple enough. So then to find 2 theta, sine 2 theta,
You would have 2 3/5 theta 4/5. So then 6/5 times 4/5,
24 over
25.
25. There you go. Yeah? Which one do you guys use for cosine? So you can honestly use anyone. Who used the first one, the 1 minus 2 sine theta? Raise your hand. Okay, who used the second one? 2 cosine theta minus 1. What about the last one? Okay, so no matter what, we still should get the same answer though, right?
Yeah.
Okay, so since no one used the second one, I'm gonna use the second one of 2 cosine squared theta minus 1. So then that is 2 times 4/5 squared minus 1. 2 times 16/25 minus 1. That is 32 over 25 minus 1, which is 25, so 7.
Yes.
over 25. You guys got that? You used the first one last one? Awesome. Questions? Let's look at this one. To solve sine 2x equals sine x for x is in between 0 and 360 degrees. Okay? Now, for this problem, one thing that you cannot do is sit there and try to divide both sides by sine. It does not work that way. In whatever mind you have, it does not work that way. Okay? Because when you divide sine, you lose a crucial answer that sine x could have been. Alright? So you don't divide. But one thing we can do is what? Plug in the identity, because sine 2x is an identity of sine 2 sine x cosine x. Okay? Now here, we still cannot divide by sine because again, we'll lose a crucial potential answer with that sine x if you try to divide there. You cannot divide by cosine either.
Divide by 2.
You cannot divide.
Multiply by 2.
Subtract what? Yes. Bring to the other side.
Oh, you gotta turn it into tangent, that's what I would do.
And then what would you do with it?
Well, you try to do something.
We're playing by ear here.
What would you do now? So we can figure out this exact
You
problem.
can factor out a sine x. Because if both terms have something in common, you can factor it out. Leaving with a 2 cosine x minus 1 equals 0. And since you have factors that are equal to 0, you can do what to those? Set them equal. So you have the sine of x equals 0 and 2 cosine x minus 1.
All this place back.
And then this goes back to the very first types of problems that we were dealing with, the ones that are a little more simple, okay? So in this first part, we're trying to figure out where in between 0 and 360 degrees is sine 0.
It would be at,
0 degrees?
Good.
if we have 360 equals 0,
It'd be in 0 and 360,
and as well as 180.
as well as 180. Anywhere else? So, don't use a circle, because answering problems like this, is then you're not sitting there trying to figure out, okay, crap, can't use a circle. So let's draw it out, let's do a quick sketch. You know it, you can finish memory. How would I solve for this one? Add 1. Now we can divide by something. Okay? Then we're going to do a similar process to figure out where on our unit circle is cosine 1/2.
60 degrees. 300.
So positive 1/2 would be in your first and fourth quadrant, so that would be 60 degrees and, what'd you say? 300. So all 5 of these answers are solutions. Questions? With these problems like this, do not sit there and try to divide out a trig function because you would divide out an answer. You would have missed all of these answers here for where sine is 0 if you had divided out sine from the beginning, okay? So don't do that. Okay? You can also use identities to prove other identities or other things as well. Okay? So we're gonna look at this problem. We're gonna prove it together, and then we should have some time for you guys to do the next one on your own. Okay? So we're trying to prove that 1 plus tangent squared x cosine 2x equals 1 minus tangent squared x. We're proving identities. For those who never proved the different things before, you always start with your most challenging side to get it look like your more simpler side, okay? So when you look at this problem here, does the left side look more challenging or does the right side?
left side.
The left side, okay? And plus, you can do a lot more to the left side than you can do to the right side. So our goal is to use our identities, things that we know about sine, cosine, and tangent, to make the left side look like the right side, okay? So we're only going to deal with the left side, and you'll see it magically forming to the right side. What do you think?
I say we mess with the cosine 2x.
We can mess with the cosine 2x first because that is one of our double angle identities. Which one do you want to replace cosine 2x with? Cosine squared minus sine. Honestly, any one will probably still have about the same level of work. Okay? You guys want to use that one?
Sure.
Alright, here we go. So basically we're trying to get the left side to look like the right side. So it's cosine 2x minus, cosine squared x minus sine x, right? Sine squared. I wrote it, but I didn't say it, I'm sorry.
Can you take that tangent square and turn it to sine squared over cosine squared?
Sure can.
There's a y, sure.
Okay.
I always get like trying to get rid of tangents. That's what I always do.
Yes, and honestly, it makes things a lot easier if you just work with sines and cosines. I know we're trying to get it to look like the tangent over there, but if we can get it to sines and cosines first, they'll magically turn it back to tangent. So let's go ahead and let's replace that tangent squared x with a sine squared x over cosine squared x using that good old quotient identity. So now that we have all sines and cosines, what do you think we can do?
Multiply.
So we can multiply here. FOIL, right? Old school foiling.
Box.
Or box, it doesn't matter. What's 1 times cosine squared x?
Cosine squared.
What is 1 times a negative sine squared x?
Negative sine squared.
When I do the inner, when I multiply it, sine squared x over cosine squared x by a cosine squared x, what happens?
Sine squared x.
Those cosine squared x's cancel out, leaving you with just a sine squared x. Does everybody see that?
Yes.
Okay? And what about the last?
Negative 2. Negative sine. Negative squared x squared.
Negative. What's sine x squared times sine x squared?
Yeah. Sine squared squared over cosine squared. I was right. Go ahead, man.
I didn't say you were wrong.
Because that is a sine squared x over 1.
They're both on top.
Because they're both on top. This is the same thing as saying sine squared x over 1.
Let's put sine in the middle.
Oh,
Yeah.
the next step, yes. So now from here, yes. We have a negative sine squared x and a positive sine squared x, so those cancel out. You see how it's getting smaller? Right in front of us? What do you think we can do here?
Could we put out the sine squared from that fraction somehow?
Also, can we incorporate tangent again and make cosine squared x minus tangent squared x? Oh, is that what they're saying? Okay, yeah.
Wait, I
Well,
returned cosine
okay.
squared x
Pull
into
that square.
If we get cosine squared x minus sine squared x, can we get that to equal 1?
Okay.
Wait, this is my question. If you have, well, if for instance, for example, both the cosines were to the fourth, like the sine is, would that be, would we manipulate our identity? How it was sine equals 1 and all that, could we do that with that as well? So if we multiply cosine squared x, then be cosine squared.
Oh, I got you.
Now, I think I heard someone say something. You cannot cancel these, okay? Because they're being subtracted instead of being multiplied, okay? But, yes, Celeste?
You go. You go.
Oh my God.
Multiply it to make a common denominator.
Yes, multiply to make a common denominator of a cosine squared x. So this first part will turn into a cosine to the fourth x minus sine to the fourth x. Get that common denominator, that way you can actually subtract them from each other. Now what? Row too big, I'm running out of space here. Now what can we do? We could, but I don't know how that might help us.
I have another idea.
Yeah, but there's no equal here.
I have another idea. I don't like this one.
Okay, what do you got?
Okay, so you know the sine 4x over cosine squared x?
Yeah.
You break that apart to where it's sine squared x over x cosine squared x times sine squared x. So that's cosine squared x over cosine squared x equals negative tangent x plus sine squared x, and cosine squared x plus sine squared x equals 1.
Matthew,
So
stop.
1
No
minus
one's
tangent squared
understanding
x.
you at this point.
Are you saying to break it
I
apart?
see what you're saying. The only issue is that it's a minus there. There's no point in time did you ever change that to a plus. So that you can,
No, I mean, okay, so
so so that you can make a one.
So
Hold up.
there.
That top part can be split up because you have both of them are raised to the fourth. They're perfect squares, just dealing with cosines and sines, okay? I do have your homework. It has not been copied. You guys stop back in at lunch. I'll leave them in my room so you guys can grab them, okay? And then I'll also finish up the rest of the problem. I'll post the video. And you guys will get that.